Good morning. Welcome to episode number 27 of the ZOOMTOWN experiment. We've been at this for over a half a year, and right now things are getting more and more interesting with all the Micropython code coming into play to make our Zoomie move around. Now, last week we went over a lot of information dealing with velocity control. This week we're going to go over a lot of information regarding position feedback and position control. And then next week we should be getting into the velocity control again. And then after that we'll see how velocity control and position feedback, how we can manipulate that to get the Zoomie to drive in straight lines and go around corners and all of that. As I mentioned earlier, the Zoomie and everything we're doing with it is all about motion control. Getting our Zoomie from one location to another location as accurately as we can. And that is a very key element of this project over a lot or all other robot or small robotic projects that are out there. And this will just keep getting to be more and more intense and more problematic the further along we get in this project. So to start with, let's go over what we're going to cover in this particular episode, and it's all about the rotary encoders. First, I want to show them to you on the Zoomie, and then we'll go into some other graphics here on the computer. As you can see, this is our encoder bracket that we worked on months ago. Here are two wheels. Now, the thing to keep in mind, here's the motor, the gearbox is in this area, and this is the wheel. And this will come into play here real importantly in a little while. But we've got the motor, which is what we control. We control that with a PWM signal to make it go fast and slow, forward and reverse. The wheel goes on the output shaft, and then in between there is a gearbox. And that can give us all kinds of grief, and we'll be discussing quite a bit about that a little later on. But at the center of this wheel is a magnet that has the poles going crossways like this instead of axial like you would normally see with a magnet or a round magnet. Now, the encoder is a module type. The chip AS5600 is on this PCB, and I've mounted it as accurately as I can, centered over that magnet as well as spaced away from the magnet or the side of the wheel. This wiring became a huge problem in my earlier version when I was using the stiff jumper wires. These guys. These are just horrendous for a lot of the projects, especially anything you're going to handle a lot or do motion with. The conductors in them are very brittle and break frequently. And I was having all kinds of grief with them breaking off of here. So since then I've used these silicone insulated jumper wires. They cost 10 times more instead of a penny. Each wire is 10 cents, but they work. So I'm real happy with that choice. But also, while we're looking at it, this encoder, there's two of them. A right one and a left one, and then they connect up into here on the top into the I2C interfaces. And we'll get a little better understanding of that when we look at the schematic. Now, rotary encoders are important because they're going to give us position data, which we can use for odometry to know where we currently are or the current position, and very importantly, the distance to go. And that'll make a little more sense in a few moments. The encoder can also give us velocity data. We can, based on the knowledge of knowing we moved X distance in a given period of time, we can determine how fast we're moving That would be velocity. And then we can use that feedback for automatic steering, especially for feedback when we're turning, because not all turning will be a simple pivot turn, or even with a simple pivot turn. We still need accurate information as to how far the Zoomie moved so that we can maintain proper heading. And that's very critical in this whole world of what we're trying to do. We've got to maintain heading and distance, and then we can have a higher probability we can get from point A to point B without driving over somebody's lawn or through their yard or bumping into another Zoomie, which could be a problem. So rotary encoders give us position data and velocity data. There's two types of encoders that are commonly used in motion control in our world and hobbyist type stuff. You would have what's called, on the right-hand side of the screen there, incremental encoders. They behave like an up-down counter. There would be a wheel with a number of, usually these are done with optical sensors, either holes or little switches or bumps. There's a lot of different ways these are made, but for every mark, we would count up or count down by a value of 1 or a value of 4 if we split that signal out into a quadrature encoded signal. But incremental encoders, they're just an up-down counter. They have no unique positions. There is no way to identify any one of these positions where you see that black mark. It's just an on or an off. And there is no rollover to deal with. That'll make more sense in a moment, but as we're counting, it's just add 1, add 1, add 1, add 1 every time we see a change in color. Now, if we're going the opposite way, or whichever way we designate as counting down, it would be -1, -1, -1, and so on. They're very simple to work with. The math is very simple. Everything about an incremental encoder is simple, except for making them small enough so we can get high resolution out of them. Now, what we're actually using is technically called a digital potentiometer chip, but we're utilizing it like an absolute encoder, and it works very well for that. What makes an absolute encoder different is each position around the whole device or around the whole encoder has a unique value, just like a clock face. There will only be a 1, 1, a single 2, a single 3. There are no individual positions or common positions. Everything is unique. And that way I can tell exactly which angle, rotary angle, this our wheel is relative to the axle. Now that also introduces something which is rollover. As you can imagine, we're going to go through from 1 to 12 all the way around. When we get back to 12, we go back to 1 and count again. That adds an incredible amount of complexity to the math for handling getting positional feedback out of it. As you can imagine, we almost need two counters, one that'll count from 1 to 12, and then one that'll count every single rotation, so that you would have 10 rotations full plus a portion of another rotation. It starts to get complicated. Then if you reverse it, the maths are inverted. And then if you introduce backlash and gearing, it gets even more complex. And we'll be touching on that a little bit later. But the important part is this. As we're going through this with the rotary encoder, we are not using a very basic incremental encoder. We're using a much more complex absolute encoder, so we just got to deal with the math involved with it. It has its advantages and it has its disadvantages. With absolute encoders, we've got to deal with understanding that there is a unique position that is 0. So if I ask it, the encoder, what position are you at? It'll be somewhere between 0 and technically 4096, because our encoder, instead of having 12 unique locations around it, it's got 4096 unique locations within one full rotation. So for a starting point, we need to, because we don't know where 0 is, we need to create an offset and use that offset to say, okay, currently the encoder's telling me it's at 150. Okay, but I need to reference that as 0. And that's where that offset would come in. Instead of it reading it directly as 150, I would add a negative 150 to that value so that it shifts it back to 0. That gets to add a little more math to counting with an absolute encoder. We would need to keep track of the rollovers in our counter, and there's a couple different ways for it. In the development of the code, I've tried it a couple different ways, and I was really looking for efficiency and simplicity, so you'll see what I came up with once we get into the code. But as already mentioned, the math will have more complexity when reversing direction than just simply counting down, and we'll have more complexity dealing with the gear backlash. And hopefully I got an idea how I can demonstrate that, so hopefully that'll work out real well for you so you can rationalize that. Now, our positional feedback that we really need is almost twofold. We need to know how far we've traveled, which would be where we currently are, our current position, and then we also will need to know how far we need to go to get to our destination. So every single motion we're going to process, our Zoomie will start at some known starting point. We are going to move along at some velocity, and at any point along this way, I will need to know where it currently is. So I need to pull this information constantly from these encoders. The distance to go will make a little more sense on the next slide, but as you can imagine, as we get toward the end of the move, it's important to know how much further to go before we get to the destination so that we don't overshoot it. And this will help you understand why. As we learned in our last episode, acceleration deceleration is going to be very, very critical for starting and stopping motions. As you saw, the Zoomie was doing these really cool forward and reverse wheelies, which look fun, and frankly, they are a lot of fun. But that's not only going to damage the Zoomie, it's going to give us positional errors like crazy. So we have to deal with it. And to deal with that the normal way, just like with your car and anything else that moves, we need to accelerate and decelerate. So now if we look at this motion, the same motion as I just showed, we're going to start. We will need to accelerate up to our velocity that we want. We will cruise along at our velocity, and then we will decelerate to a stop or to a lower velocity as we approach our destination. We can't wait till we get there and then start slowing down. So this is where that distance to go really comes into play. We need to calculate how long or how far of a distance it takes to get from this point to this point, so that we can decelerate down to our stopping point at the moment we arrive at destination. This, I will say right out and right off the bat, hopefully I can find a link that I found that really helps explain acceleration way better than all the other scientific approaches to it, where they always reference as a rate of change over every second per second. And that really screws up a lot of people, because we're thinking the way that's written and always presented, we're looking for the square of something. That isn't really what they're trying to communicate in it. Acceleration deceleration is a rate of change over time. And that's the key to it. So I won't go into a lot of theoretical on it. I just will only explain how we get to where we want to get to, and how we can calculate acceleration and deceleration distances. So hopefully this gives you a good idea of what we want to do with our rotary encoders. They are very cool little devices. They're used in a lot of different things. And in our case, they're going to help us in a very critical role for getting from point A to point B. Now, as I mentioned, these are I2C devices, these AS5600 encoders. Now, unfortunately, the way they're set up on the module, they both use the same I2C ID value or ID number. And as you probably know, you need different ID addresses for each I2C device operating on the same channel. To get around that, the people, I want to think of it this way, the people that created the PICO said, oh, this comes up all the time, so to get around it, we'll let them have two I2C channels, so that if they got a device and they need two of them with the same ID, you run one on one channel, the other on another channel. And that's what we've got here that I'm showing you in our schematic. So we've got our I2C channel 0 shown above, and then channel 1 below. The upper one is my left encoder, lower one is my right encoder. Connections are, we need 3.3 volts and 0 volts, SCL and SDA for our data and clock lines. Those connect straight into our Pico W on GP0 and 1 and GP2 and GP3 for our interconnects. And nothing else is really required in it. I just connect them straight up like that, and they work like a charm. Now, as I mentioned earlier, the encoder has 4,096 discrete positions in one full rotation. And that's noted here in the data sheet. And I will admit this data sheet really requires careful study to extract the information out of it. This was the one piece that I really needed as I'm using a library for this AS5600, and thank God somebody else wrote it so I didn't have to. And I'll be giving you link information for the source of that as well. For us, all we need to do is ask it positions, so to speak. But here's where we get into it again. It's a 12-bit programmable contactless potentiometer. So kind of, I understand what they're doing with that and what its purpose is, but boy, it sure does a great job for being an absolute encoder for other purposes as well. Now that 4096 is an important piece of information, because that tells me for every increment on our encoder, I can then calculate the distance the Zoomie will move if I know the circumference of the wheel. I believe we've already looked at this chart here, this spreadsheet. I call it my place and time calculations. My wheel diameter is 1.56, and our circumference, which would be our inches per revolution, is 4.9009. Now this number isn't precise to the actual wheel. I have to fudge that a little bit. These are 3D printed wheels, so I'm looking at going out to almost a micron in the metric world of precision with that calculation there, but in truth, it's got to be really fine-tuned to the actual 3D printed wheel. This is theoretical. But if we know it's 4,096 increments or individual incremental points along that circumference of 4.9009 inches, so if I take that and divide it, as I do here, I'm going to take that divided by that, and we end up with 0.0012 inches for every count of that absolute encoder. So theoretically, I've got 1/1000th of an inch. For those of you not familiar with that, that is 1/3 the thickness of a piece of paper. I've got that fine of resolution for positional control. For those in the metric world, it is 0.03 millimeters. So it's a very fine feedback from that encoder. And that's how I'm able to, or that is why I kind of went with this absolute encoder as opposed to an incremental encoder. At this size, an incremental encoder, which would have been much easier to use, the cost goes way up in this miniature size. So it's a cost savings issue to go with the absolute and have to deal with it in the more complex mathematics. So that should give you a real good idea of everything that went into getting us to the point where I had to code it and what I need to get out of it. So now we'll move on to the other more interesting part. Before I dive completely into the code, let's first see what we're doing with the Zoomie right now. Now I'm going to play a little bit of a trick on you here. I've also got the rest of the velocity control working in here so that the car is actually going to drive, or the Zoomie will actually drive very straight. I won't be explaining that portion until probably next week or the following week. I just want to focus on how the encoder reads the position and feeds it back to us with a useful value. So when you see the Zoomie go along here for this 10-inch trip, 10 inches, 250 millimeters, I believe that would be. As we go along that trip, it'll go relatively straight. So as you saw in last week's video, the thing was wandering all over the place. Magic is happening, but I'll explain all that next week. For what I want to do right now, I've got two markers set up here, two little circuit boards, and I got a little point going to a spot here on the Zoomie. And I just want to show you that I'm going to tell it to move from here to here, which is 10 inches, as we can see here. And it will start here, and it will end at that 10-inch mark. So we'll go ahead and run it. This will take a second to get everything all going, and goes exactly where I want it. Now, if you've got a real sharp eye, you will have noticed too that it did not jerk real hard on either the start or stop. So automatic acceleration, deceleration is also in play here. But again, let's only focus on our positional feedback. So we'll do that one more time here. And then I've got to set it up for another demonstration, which I'll have to code in. Here we go for another straight move. And it works beautifully. Now I want to set it up for another demonstration to demonstrate what backlash is if you're not familiar with that term, or how badly it will affect us, because understanding both of these conditions right now will help you to understand what the code's actually doing. Okay, so let's figure out what this mysterious backlash is and why it's such a nightmare for us to deal with. First, let me demonstrate it. Now, this might not make sense if you've never handled a gear motor, but I'm going to just very lightly rotate the wheel. And if I get this right, you'll see that little dot right there, how I can just very gently move the wheel, and it seems to stop there, and it stops there. Just like that. See that? That is backlash in the gear. Now, at this point, when I pull on it and it gets to that stopping point, that's when all the backlash is out of the gearing in that direction. If I push on the wheel, now I'm going to pull it this way, and that will take out the backlash in the opposite direction. Well, if you don't account for that in certain calculations, you're going to be way off position far more frequently than you can imagine. Now, how much is that? that might be $1 million question. And why is it important? It doesn't look like much, right? My goodness, that's only just a little itty-bitty wiggle there. Well, I'm going to take the Zoomie and I'm going to drag it backwards so that all the backlash is pointing back. I wrote this little program here. I call it Backlash Demo. I'll provide that for you as well. Configure the I2C interfaces and start up and configure the AS5600 encoders. We'll cover that in the actual program, but I copied it literally out of our Zoomie-05-C program that I'll be publishing with this episode. But all we're really doing is this right here. I'm in a while loop, and I'm going to take and read the left encoder angle and the right encoder angle using these methods. I will then print it, sleep for, oh, no wonder that was going so quick. Let's change that to about 0.1 seconds. We'll sleep for 1/10 of a second and then repeat. And then we'll see that displayed down here. So I'll give us a little more room so we see more history. Okay, that is the current rotational position of each rotary encoder. As I mentioned, each position or each rotary position, all 4,096 of them, has a unique location. So I've pulled it back, and we're just seeing maybe a thousandths or a 0.0001 change on that, or 1-digit change. I'm going to push it forward, and you'll see that this one on the left, right here, changed about 30. From here, 316 to 319. That is the backlash. I'm going to do that. We'll look at the right one, 2986, 2941. So about 40 units of backlash. If we go back to our calculation table, that would be 40, we'll use our larger number, 40 times that, or 40 thousandths of an inch, or 1 millimeter. Doesn't seem like much, right? Well, imagine if that backlash presents itself as it's moving along. So in other words, we're moving along and I'm steering the robot to decelerate. Well, the robot still has inertia or momentum pushing it forward. Even if I speed up a wheel or slow it down, I'm going to move the wheel, and that will affect the encoder. Now, most of the time, that really won't matter. You know, we're going to be off by a millimeter at most. But you do that 30 times over a 10-inch distance, and all of a sudden you got a huge problem. Worse yet is we have to look at the encoder counter. Remember, it's a rollover, 0 to 496, back to 0, 496, or opposite in reverse. Well, I look at that. If I see a count going from 4,090, the next count is 10. Well, I would know that I'm going in the forward direction and I need to increment the rollover. Same thing going in reverse. Well, if this backlash is taken out during that period of transition, the math all goes crazy and you can't keep track of where the Zoomie is. So this aspect of dealing with geared motors as opposed to stepper motors pretty much have zero backlash. Servo motors deal with this because the encoder is attached to the motor, not to the output device all the way at the end. It can be done that way, but that's another control loop. So what we have to do is deal with that any which way we can. And you'll see there's a if-then structure I had to come up with to work through that, because in certain conditions that rollover we've got to account for it as normal. In other conditions, that rollover we have to ignore because it's just the backlash giving us trouble. So I think by now you got a good amount of groundwork so that you can understand a little bit better of what's happening in our positional feedback control. So now I'm going to start going into the code, and we're going to cover a variety of different topics because we got to cover our I2C and a few other things along the way as we get into how we actually run this demo. Now, I will be glossing over, and I will not even be covering anything to do with the velocity control other than a few places where we set a counter up, so to speak, or a flag up in some of those routines. Now, one of our libraries we have to include is I2C, and then this is our AS5600 library that we import. That'll gives us control over these rotary encoders. I'm going to zoom down here because all this is the same, and then we get down to this section here, configure I2C devices, our AS5600 encoders. As mentioned, they use the same ID, so we run them on two different channels. So we create two channels for I2C. So we're setting up our SDA, SCL pins as 01, ID as 1. We're going to create I2C object using this part of the library. We'll give it the ID, SDA, and SCL pins, and we're going to set the frequency to 400,000 or 400 hertz. We will do the exact same thing for the second channel. Same thing, just configuring a different channel. That allows us to run two devices with the same ID value, or however you want to phrase that. Then here I just print out the data from the scans, etc., so that we can look at it during boot up. It's very helpful during debugging. We're going to then start up and configure the encoders. We'll do the left encoder first, calling out the AS5600 library or object and providing it the I2C information and then the ID number for this particular encoder. We'll scan that value here, and then we're going to read its current position, left encoder position, and I put that into the encoder angle variable. Same thing with this one here, the previous position. Now, as we're working the math on this, for dealing with this absolute encoder, I need to know what the last reading was and what the new reading is, regardless of how much time has passed by. So we have to call this thing fast enough and frequently enough. We need to read it so that I don't have a complete rollover before I read it again. That would give us really messed up counts. And that would be true of both incremental or absolute encoders. In our case, if we let it go a full revolution, oh boy, that'd be a nightmare. I'm going to do the same thing to get our right encoder set up and running. And it too will have these global variables, right encoder position and right previous angle. Based on that, I'm looking at how much movement there was from where it was to where it is. And that covers that. And we'll be listing some of those in here. Here's our list of global variables. Yeah, I know everybody hates them, except for me. I love them. But here's our left encoder, right encoder, left encoder angle previous, right encoder angle previous, and then several others all dealing with this positional information, working from either an angular value or an offset for a linear value. Then we've got our constants. Remember earlier I said distance per rotation in my spreadsheet was 4.9009. So far in practice, I believe the actual true circumference is 4.8825 inches. So it's enough different where it bothers me a lot. It was, let's see, that'd be about a half a millimeter or 20,000ths of an inch range. And then distance per count, and that gets calibrated over time, and I'll be fine-tuning that through this whole development process. And then wheel spacing, we don't really need that right now for position, but we definitely need that information as we're working out ratios of velocity for each wheel so we can make turns precisely. So that is most of the positional variables that are global variables that we're using in this process. Again, velocity control, I'm just going to blow over that except for these two functions, which I don't believe we talked about in the last episode. When we want to make the Zoomie move, we need to tell each wheel which way to rotate, either forward or reverse. And then this device or this function, each of these functions will set another variable, global variable, left direction and right direction. That is used then in our positional computations to know, okay, it's supposed to be moving forward, but my math is showing I'm moving in reverse because of the backlash. So then I can make decisions based on that information to make a reasonable assumption that I am going forward, and that backlash, just ignore it for now because eventually that will be factored out of our position, simply because we're going to pick up that backlash going forward further down the road. But that's all these two functions do. They set the pins so that the motor drive can make it go forward or reverse based on what we want. A lot of this other code in here, this is what we're going to be covering next week. I had to leave it in here or I wouldn't have been able to do some demonstrations that would make any sense. Now we're going to get into some of the more complex things regarding position control. I've tried my best to comment this information in here. In the final encode, I'll probably strip all this out because this is just repeated essentially from our global variable list. That's this area here. Then this here is just some calculated data that I was working with that changes fluidly. So these are actually, at this point, we already know this is outdated information. But I find that when I'm working on complex projects like this, if I keep track of constants in this way, I can see things moving one way or the other. I can then know a trend. It's constantly I'm changing or adjusting for a smaller value or a larger value, as opposed to just simply changing it and then you change it again a week later, but did you go back to the original number or are you trending in a direction? That could tell you a very important story on how to fix a problem. But our first function here is probably the simplest, so we'll go through it rather quickly. We're going to, of course, give access to all these global variables, and the purpose of this set zeros, we're going to zero the encoder in position while accounting for the existing position of the encoder, which is almost never zero. As you saw when we turned it on in our backlash demo, they were two random numbers seemingly. It was just showing the position it's currently at. Now this routine has to be called before each move. We're actually keeping track of our position based on how far we move for each move. And then elsewhere we'll deal with taking that amount and adding it to a position and taking into account the heading. We are going to set our offset values back to 0 at this point. We have no offset. We're going to set our position registers to 0. We are going to set our encoder tracking variables. We mentioned those already earlier. Left encoder position and previous angle. We'll set all that to what the current encoder position is. We're going to get current raw position, and we're going to send it the flag no. That'll make a little more sense in a minute. And this is we'll spend quite a bit of time talking about that function. We are then going to print out some data just so we can observe the behavior of what's going on. Now, based on that, I can get a raw positional data, and I can take 0 minus that to get our offset. So this is how I literally calculate the offset. The encoder reads this, but I actually need it to read 0, so I just take 0 minus that, and then we'll add that value to our position. It's kind of weird, but it makes a lot of sense when you start tinkering with the math. We're going to print that out. Then we're going to get the current raw position, this time saying yes, and then we'll print out our L position and our R positions. So this function here, you'll notice we actually call something else to do a lot of work, but sending it a flag is either no or yes. That's where it's going to get interesting in this next function. So that was get current raw position. That's this guy here. Now I'm going to scroll through it first so you get an idea. We've got global data up here, and then we're going to have a change amount calculation. And then if L-dir, remember L-dir, we're setting the left direction prior to any given movement, so we know whether we're moving forward or we're moving reverse. If we don't know that, we cannot work out the math as to whether we're counting up or counting down, meaning we're physically going forward or physically going backwards. But in this case, we're working on the left wheel, making all these decisions. And you'll notice that there's if, else if, elif, else. This has to do with handling all that rollover, including accounting for backlash. Then we're going to calculate a change again that we'll be working with on the right wheel. Each wheel has to be calculated, computed, and tracked independently of each other, because if we're turning or making steering adjustments, we know one wheel has to go faster or slower than the other. Oftentimes that's intentional because we're forcing a turn. But again, we would have two different sets of calculations for a forward movement or a reverse movement. We get to this point, and we are going to set our previous left and right encoder angles so that we can then make another computation later. And then here's where that if set zeros equals yes or no. That comes in all the way back up here, set zeros, and it's passed in here. So we want two different things to happen depending on how we're setting these zeros. We need to do something first to get data. Then after we've got that data, we can calculate all the offset data and update positions, and then that's when we want the yes function to go on. Like I said, this is a very involved functions to get a simple position out of an absolute encoder. So with that, let's kind of try to cover a lot of this. The global variables are explained over here. I don't think we really need to, well, let's take a look at a couple of them. This is right here. Right position, account for rollover in either direction, 4096 to 0 or 0 to 4096. That gives us our forward and reverse calculations. But this position here is, this variable here is how we're going to deal with that. Sometimes we have zero movement or we have backlash in the gear. That's what these two variables help with. And let's see, calculate wheel position from encoder reading. So that'll be put into here, and then if needed, add in offset data, and that'll be further down the road. Okay, so now, right here we're going to start out by reading both encoders. There's a function or a variable here, and that read will be put in here, and that'll be a value between 0 and 4096. I've got a debug flag here for when I'm working on some issues that have popped up. We're going to calculate the chain, and we're going to calculate the difference between left encoder angle and the previous left encoder angle readings. This will be an amount that's some amount between 0 and 496 between two different positions. In this case, we'll assume we're moving forward. So now if the left encoder angle is greater than it previously was, we would take and calculate or store the left encoder minus the previous angle. And if debug was on, we would print it out. But all I needed was the LC at this point. Left count, think of it that way. Now, if the left count or left encoder is less than the previous count, and the amount changed by more than 5 or 4,000, then we must have had a pretty serious rollover, right? Because a change greater than 4,000's a lot. But when we're going the opposite way on a rollover, that's not so much. In that case, our left wheel change is we've got to account for the rollover amount. So we're going to take the left encoder angle, add 4096 to it so that the math works out correctly when we subtract from that the previous position, previous encoder position. And again, if debug, print it. Now, if the left encoder is less than the previous encoder angle, we're going to treat that as a non-movement. We're just going to leave it as is. That'd be just a small shift. Any other possibility that would have went on would be we want to set the left counter to 0. These are little conditions that occurred probably due to backlash, but resulting in, truthfully, 0 movement. So we just don't deal with it. We don't have to account for that 0 movement within our positional data. Now this was forward. This is reverse. In reverse, we're going to really invert the math. We're counting down or backwards, so to speak. So here is just the inverse of that mathematics. And the rollovers get a little more confusing because here you'll see that I add the 4096 to the left, but because I'm going backwards, counting the opposite rotation, I add the 4096 to the previous encoder angle. And that way we handle our math properly. And again, that flag of 4000. Counting up a lot is an actual rollover is the way to look at that. So that's our left wheel. Our right wheel is exactly the same thing, but it's, let me make sure of that. I was just going to say, I think it's inverted in the math from left wheel to right wheel as well, because one encoder is rotating this way, one's rotating this way. So we'll just make sure that real quick. This one's less than, and that one's greater than. So yes, the math is inverted from left side to right side. And we're going to get all the way down to here. We will update our previous encoder variables so that the next time we come through this loop, we can work from previous information and new information. If set zeros is yes, we will perform these calculations and add in the offset, meaning this is normal running. But if it's set to no, what we want to do is get rid of all that. Offsets are already accounted for in position variables. So we don't need to do the, where did it go? The L counter calculation on that. So this is normal running. We're adding in the offset. Here we're just trying to get a position value essentially without the offset. And then we'll return that as LC and RC, left counter, right counter. Also in here, you'll notice that this L position, R position, here and here and here, this is where we take into account or convert the value into linear distance moved. All the other math up to this point has literally been rotational information relative to how far the wheel has moved or rotated. Here you can see that our distance per encoder count, is factored into the positional data so we can get linear positional information. As with the other ones, we've got our global variables declared at the top. We're going to record our previous positions before updating. We will have LC and RC called up to get raw position information from here, and that would be this information, not this one because we're passing in no. We're going to calculate the incremental distance for left and right wheel based on current position and previous position. Then we're going to come up with a factor that is 1 divided by the main loop cycle time divided by 1,000,000. So cycle time divided by 1,000,000. That is how we're going to work with getting velocity data. So with that, our left incremental distance times factor will give us our left velocity, and that is in inches per second. Then we can do exactly the same thing for our right wheel's velocity, and that, of course, too, will be in inches per second. Next up, we're going to calculate the left distance to go and the right distance to go, and that is simply a matter of subtracting the left distance to travel minus the left position. And that's where it was versus where it is. Or, I'm sorry, where the destination is minus the current position. Then I've got a couple other little calculations here. You'll notice that I've got them flagged as debugging only. I was looking at the left and right differential. That would be left position minus right position. Not real useful. And then the difference between the round of left position minus right position rounded off to 3 decimal places, and that was so I could print out the data and see it a little bit more organized, so to speak. And finally, this whole function here, fetch position in inches, returns the left velocity, right wheel velocity, left distance to go, and right distance to go. And that's for each wheel. Now we're going to go all the way down here, and I'm going to just point out a few things here. The motion segment processor function, we're going to go into a great deal in that, or on that, in a few episodes further down the line. This is how I will be setting different types of motion in up for processing. In other words, if the motion is forward with encoder steering, I would set all these parameters, and then once that's done, the motion would begin. We're just using this one right now for our demonstration purposes. You'll see I got a couple here I don't even have set up yet. Trip executor, that's only kind of just dropped in here again for us to put together a simple motion and then run it through the processor. And again, this will be explained in greater detail later, but this, I'm saying load a trip plan. This would be taking data from MQTT that came from the scheduler, converts it into a list of motions to perform, and that's kind of what we're seeing here. Essentially, forward encoder steering is a type of motion, and it's going to go 10 inches, and that's what we ran here. And then the third parameter I'll explain in greater detail later. This is a function that will run whichever step of the trip plan is being pointed to with the trip plan pointer variable. And then that once that executes, it'll advance the pointer. I think it was right here. Okay, this is where, for this debugging, I said load the trip plan and then execute the trip segment. And I actually started that before we even get into the loop. And then from there, everything starts happening in our loop. And there are a couple of things here I wanted to point out. That is something in process of testing. Handle positional feedback processing. This is where I actually call the functions to get the positional data calculated from the encoders, calculated and offset and all that fun stuff. So that's performed here at the start or at the top end of our main loop. These CP1, CP2, 3, 4, 5, 6, those are just calculation points for cycle times, so those won't be in there in the final code. But another important function related to position is calculating the center line distance to go. And that is very important to know where the Zoomie is at any point along the way. Now you would think, well, it's simple. If you're going in a straight line, it's the same distance for left wheel and right wheel. Well, keep in mind, I will also be going around curves, so I need to know where the center of the Zoomie is, average position between left wheel and right wheel. And that's what we're doing here. Left distance to go plus right distance to go divided by 2 is our average at the center line of the Zoomie, and we would call that our distance to go. And that is the flag that we would then also use to initiate deceleration. Remember all the way at the beginning of this, it was probably like 3 hours ago, where we got that trapezoidal shape where we ramp up at the beginning of the motion for acceleration. We cruise along at a fixed velocity, and then at a specific point in time, we need to decelerate. And that exactly is what this is for. It tells us, or provides us that point where from here start decelerating based on all the other calculations that will be associated with that once we dig a little deeper into velocity. I am doing automatic velocity adjustment here, and that's how the steering kind of knew how to keep the Zoomie going in a straight line for this test. And that'll be explained in much greater detail later. The last thing we will do with this is I am going to modify some of this code. We'll run the routine again, and then we'll update all of our criteria, all of our statistics up here at the top, because I haven't done that in a little while. And I think it's important that I get this all reconfigured and updated with what we're doing. At the bottom of my main loop, I've copied these down into here so I could work with them more easily. And I've gone through and recorded the times for all these. This is our last one, and then we can look at the current status of how long it's taking everything to operate. Now keep in mind, there's a number of these functions in here, like adjusting the velocity, etc., that are occurring that we haven't even discussed yet. So we're a little bit ahead of ourselves on this particular test. But we'll move this up. Let me copy that. Move that up. We'll run it. Get my cursor all the way back at the top. Okay. 23's our peak so far, 19's our low. So I'm going to give it about a 20 on that one. That's 20 microseconds that you're seeing there. So 0.020 and m seconds. That's milliseconds now. And that is that function. Now total all this stuff up here. Through the magic of editing, this will take a second. And we are currently at 2.204 milliseconds for our total loop time. Still well under our 5 milliseconds that we were targeting. Still got a lot more to go though. As you can see, position control and dealing with the absolute encoders is a lot more intensive than just simply dealing with an incremental encoder where we count up or count down. There's a lot more to it. We've got to take into account the gearing backlash and a number of other issues that added to the complexity. But nonetheless, we've now got the ability to count how far the Zoomie moves and verify that against the command. So we actually can say go 10 inches and verify that it actually went the 10 inches. That's going to be really, really important as we move further along with this whole project. So at this point, I have no idea how long this video is. I know I've been chatting a long time, but I think we'll wrap up this video. And next week, I believe we're going to be working on velocity control, tying in the rest of the bits and pieces with that one. It'll probably be a long, complicated one as well. Look forward to seeing you next week. Thanks for watching.